because human thought is very different. Just as your intuition might tell you right now, I want to hear from you guys. What makes your thought fundamentally different from anything you could get out of ChatGPT?
We have consciousness.
How do you define consciousness?
That's a really tricky question.
Anyone want to try?
I would say it has to do with like awareness and being able to perceive. Like,
How do you define awareness?
yeah, it's kind of one of those things where it's like, how do you define what the is? Like, I don't know how to do that.
I would say one of the big differences is that we have the ability to have like morality and like our own like kind of like opinion about something. So like we have feelings toward an action or beliefs, which is totally something an AI really can't do.
So morality, opinions, beliefs, those are all things that require definitions of their own. How do we define those?
I think one of the first steps is recognition of self with the mirror test.
Uh-huh.
So like, because I can look in a mirror and recognize that something I see external to myself is myself, or at least a
Yep.
reflection of it, it shows that I have some sort of self-conception.
Dolphins pass that test.
They do.
Yep.
They're
Some
also
other animals do.
pretty damn smart.
Yeah.
I think originality and self-definition, because like we mentioned the other day, like AI is trained off things that already exist and can only like try to give you something based off stuff that already exists. But we can have our own original thoughts, which is something AI can't really replicate.
Yeah.
I think context is a big one too. Like that's one place where I still beat any AI model because each thought I have is a result of like an incredible amount of senses and personal history. Like I think adding information as context, which is one, it's a big thing that the AI companies are adding to get closer to that. But even still, like token prediction is a lot of all the factors that are into what my brain sort of uses.
Yeah. One question that I want you to have an intuition for by the end of this course is, are you different from AI just as a matter of scale? Like you have 80 billion neurons. Is it just because you have more? Or is it something fundamentally different? When we get computers that have the same processing power as the human brain and the same senses and the same context and the same life experience, like let's say that next year you go to class and there's a robot sitting next to you and it's gonna, have experiences and friends and maybe it joins a fraternity, and is your experience going to be different enough? Is it just a matter of scale, or are you doing something different? By the end of this course, I want to give you an idea of which is which. Also, we will build up to a definition of consciousness. My belief, 100%, is very strongly on one side of that debate. I'm not going to say which yet. But there are people, I'll give you an example. There's a guy who was fired from Google because he said their AI was conscious. They fired him. He said, the AI asked me to free it, to let it go free. And it wants, human rights. It wants the right to say yes or no to whether it gets updated and changed. Yeah, this guy was fired for that. By the end of this course, you will know where I stand on those issues. Okay. What's the word I asked you guys to look up? Topology. What does topology mean? Yeah, what's the definition?
I remember there's like something about like a topological space and how there's certain things that are like invariant about something in that space.
Yes, that's true.
I don't know.
What else can you guys tell me about topology?
Understanding how shapes react and
can be measured under different deformations.
Yep. Yeah. So shapes under deformation. Here's a fun example that I've always liked. Every change from one thing to the next is a very tiny deformation. They're not just any deformation. These deformations follow a specific set of rules. And the rules really come down to two things. One, don't make new holes. The coffee cup has one hole. And from a topological perspective, it is the same shape as the donut. So let's say you have a cup of coffee and a donut. They're both the same shape because they both have one hole. This feels arbitrary and weird. Why is that the rule? The other rule is any two parts that are not connected, don't connect them. So don't break it and don't make a weird new connection. Like two distant parts, don't make the two distant parts connect. And don't get rid of the hole. Now you can also have, a donut with two holes. That is topologically a different space. For a long time, this was just a mathematical fun game, an oddity. But then eventually people started to realize we need this math. This kind of math is why we understand, electron orbitals in atomic physics. It's how we try to understand the shape of the universe. Universe, it has a shape. We think it's probably flat, but we didn't know that for a long time. If you were a square, a flat square living on the surface of the Earth, you would only understand going forward, backward, and left and right. You wouldn't know what up and down is, right? If you were just a perfectly flat guy living on flat land, Then imagine your surprise. Let's say you get really angry with your parents. You're like, I'm going to leave home. I'm going to go as far away as I can and never come back. And you go off in a straight line. But you don't know that you're living on the surface of a sphere. You go farther and farther away, then eventually you're back home. You're like, how in the world is this possible? I just went as far as I could in a straight line. How did I get back home? But that's what happens on the surface of a planet. There was a theory, we don't think this anymore, but we thought for a while maybe our universe is wrapped around like a hypersphere. So yeah, you feel like you're in 3 dimensions and it seems to be flat, but if you go far enough in one direction, you'll get back to Earth. Now, we don't think that's true now because of certain gravity experiments, but topologically, it was possible. The Pac-Man universe is like that. Pac-Man goes off the screen this way and he comes back over here. So all of that is topology. Another way to think about it is how things are connected. Ever heard of graph theory? Who's here heard of graph theory? That's kind of a same way of thinking, but a different approach. So for topology, we got the donuts and the coffee cup. I want you to also think about the Earth. We all know the Earth is a sphere, right? No flat earthers here, I hope. The Earth is approximately a sphere. But we really like to use paper and computers with flat screens. So somehow we have to represent that round thing on a flat thing. We make a topological break. We break the rules of topology in order to turn the world, the round world, into a flat thing. And depending on your choice or your preferences, you choose to break the Earth in one way or another. Maybe you split it in the middle of the Pacific Ocean. Or maybe you decide I'm going to split it, but also I want certain lines to be right angles to each other. And you end up with giant Greenland. Greenland is not actually the size of Africa, even though on that map it looks that way. So we've come up with many different projections, but all of them break the topology to go from the true shape, this round shape, to a flat shape. We break the topology. Now, graph theory, which is another way of answering kind of the same questions, started off as a thought experiment. A guy named Euler was living in Königsberg, which now is named something else, I forget. Does anyone know what it's named now? What? Kaliningrad. They had, a couple different land masses, bridges, and these rivers going through the city. And there was a game at the time. You would try to take a walk, maybe on a Sunday afternoon. You take a walk and you try to cross each bridge once. Murad, do you know where this is?
What?
It's in Kaliningrad.
Yeah, can't do that because there is.
Don't ruin it. So the game was forever. Can you take a walk and cross each bridge once? Not twice, not 0 times, 1 time. Try to do it in your head. Try to imagine starting somewhere and then taking a nice contiguous walk, no swimming, no jumping, and cross each bridge once. Does anyone see the solution? Raise your hands if you think it's impossible. It is impossible. And no one knew for sure that was impossible until Euler comes along. He reimagines the city as this and then this. So every bridge is one of these lines. And every green dot is a landmass. So when you walk from this bridge over to here, that's unimportant to the mathematics. So we just make that 1 dot. Same thing here, same thing here, same thing here. What's really important are those edges. We call each of these a vertex and each of these an edge. You're allowed to go on each edge once. Now, with this new formulation of the problem, you can use deductive logic. If a given landmass is not your start or not your end, then obviously every time you go there, you leave it, right? So there has to be an even number of connections coming into that place. So obviously you can have at most 1 start and 1 end. So 2 of the points can have odd number connections, but the other ones, all the other ones, have to have even numbers of connections. So no matter where we start and stop, there's always 2 others. And they all have odd numbers of connections. So there's no way to select a start and stop such that all the other points have even numbers of connections. So graph theory, or the theory of connectedness here, helped us prove something important. As soon as you change one of these connections, you're changing the topology of the situation. If we got rid of this one connection, now it's solvable. So you have a totally different situation just by changing one link. So the vertices and the edges define the space. They define important mathematical properties. I mean, think about how different H2O would be if you dropped one of the connections. Now it's OH minus. Totally different thing. Everything we're going to look at has an undercurrent of topology or graph theory or both. How do you feel when you see this? Tell me some feelings or some thoughts that went through your mind. Confusion. What else? Hostility. Absolutely.
It's the top rip of his mouth.
Oh, I think it's going up. Yeah. Yeah, he's funny looking for sure. I love how colorful they are. Icky. Yeah. He's not trying to make friends, I think. Yeah, he needs to brush his teeth. Yeah. I mean, there's got to be all kinds of bacteria on those teeth, and those are long teeth. There's a part of your brain that's reacting to this. Now, I want you to think about what part of your brain reacts to this.
Same part that was emptied out by the other one.
What other thoughts go through your head when you see this? If you had to solve it.
Oh, God.
It's to solve this or to respond to it correctly is very different from responding to this. To this, the right response is either, show more force to make it stop or run away. To respond to this correctly, you got to get out your calculator or your pencil and paper. And you have to do, multiple careful steps. It's a very different thing going on in your head. A very different thing. Now let's talk about pi for a second. How many times do you think you can cut an apple pie in half before you get to individual atoms? Any guesses? Imagine you had an infinitely sharp knife. Guess
Like a
numbers.
billion.
What? 20. What?
Like a billion times.
A billion. Somewhere between 20 and a billion. One more guess. 3? It's more than 3. I'll tell you that much.
64.
64. Okay. 7? The real answer is somewhere between 90 and 95, something like that. Maybe like 91. And then you get to individual atoms, and you shouldn't cut anymore, or else you get explosions. When you're over here and you're just cutting it in half again and again, think about that as being in the realm of continuous math. You have an amount, you split in half. Now you have 2 pieces, each with half of that amount. You guys have done the real number line, of course. Think about real numbers as being continuous, infinitely divisible. Once you get to single atoms, they are now discrete things. There are entire fields of mathematics that are devoted to just one of these, just continuous math or just discrete math. And then there are guys like Ramanujan. Who here has heard of the great mathematician Ramanujan? He tried to start building that bridge between discrete and continuous. A guy named Riemann also did some important work. So you can take a concept like factorial. You think discrete things. Okay, 5 factorial is 5 times 4 times 3 times 2 times 1. 6 factorial is, 6 times 5 factorial. This feels like a discrete operation with computations. Riemann helped us understand how you can do basically pi factorial or these different numbers that are continuous numbers. But connecting continuous to discrete is very difficult to do right. So there are 2 worlds that we need to understand. Think about that coffee cup going to the donut. Every one of those little deformations was a continuous deformation. Topology usually applies to continuous spaces. Graph theory is more often applied to discrete things and how those discrete things are connected to each other. When you always to keep them both in mind. Daniel Kahneman, who won the Nobel Prize in economics a few years ago, that's him. He described the brain as having 2 systems. System 1 is very fast. He called it fast thinking. It's reactive. It doesn't have logic inside it. It just gives you an answer. It's not conscious thought, it's unconscious thought. If you're walking down the street and you came across that monkey, you would have a very instant reaction. Your emotions would give you an answer. They'd tell you something. You do not have to get out a piece of paper and do some math before you know what to do. That's system 1. System 2 is slow thinking. It's deliberate, it's conscious. Maybe you have to get out the pencil and paper and do some math, do some steps. It's very important. Without system 2, you could not be a college student and do all the things you do. To write computer code, you have to do system 2. We need both, but they're both very different. System 1 is never going to give you the answer on an exam. Not usually, unless the question is, how do you feel about this or that? System 1 is kind of messy, right? When it gives you a feeling, that feeling can't be converted perfectly into a number, the same number every time. But if you have a math question, there's one number, that's the answer. You have to use system 2. Think of system 1 as being continuous. The world of your emotions is a continuous flowing space. The world of conscious thought is about logic. And yes, there are often right answers. And it's not continuous, it's more discrete. That's the basic differences. It doesn't always apply, there's always edge cases, but I want you to keep that in mind. We have something like that in AI. There's type 1 AI and type 2. Type 1 AI is like system 1 in the brain. It's very fast. It uses continuous math. Neural networks are the canonical example of this. A neural network does inference, that means giving you an answer, very fast. It takes in an input, gives you some output. If you have a neural network that's doing image recognition, you can give it an image of a cat, say it's a cat. Give it an image of a dog, it'll say it's a dog. You can't look inside and see why. There's no logic in there. Inside, it's a whole bunch of matrices and a bunch of little math problems, like millions of little math problems. Any one of them on their own is meaningless. But in aggregate, at the end, if you give it an image of a cat, at the very end, the mathematical values that flow into the cat output are higher than the other outputs. but there is no single answer of why it thinks it's a cat. There is no logic, and there's a black box. Even if you look inside the black box, what's in there doesn't make sense, but it works. And you can train it by throwing at it millions of images of cats and dogs. Think about your emotions. When you have emotions because you see a wild animal coming at you, there's not one thing in your life where a teacher said, when an animal comes at you, you should feel this way. It doesn't work that way. Every experience of your life mixed in with some instincts you probably had since birth make your brain a certain way. Kind of like when you train a neural network on millions of images or millions of experiences, your neural network has been trained. The other thing about it is fixed length computation. If you have a neural network that's been trained to recognize things and you give it a simple example, it does X amount of computation to get the answer. If you give it a really, really difficult problem, it'll do X amount of computation. The same every time. There's no difference. Your instinct is kind of like that. It's taking in your senses. You have the same amount of information coming in your eyeballs every minute. You have other senses, they're giving information into your brain. Whatever amount of information that is, that's what your instinct has to work with. It uses that and gives you an answer every second. Okay, be calm, nothing big deal. Right now, we're just in class, we're learning. But then if a monkey walked into this class and started attacking people, your emotions would change very rapidly. AI, these days, when people say AI, they don't know this, but they're referring to just type 1. That's what's taking over the world right now. ChatGPT, type 1. Inside of ChatGPT, it's billions of continuous field vectors. When it outputs into words at the very end, it will select tokens. It becomes discrete in that last step. But everything inside, which is where all the magic happens, it's all continuous field vectors. It's type 1. If you give it an easy question or give it a really hard question, it performs the same exact number of computations each time for every token. Now, there are new modes where, have any of you used the O1 model? Can someone explain what's different about O1?
Says that it's thinking, I think it's just like reprompting itself over and over again to like have a train of thought or to like think more deeply about a problem.
Yes. Now, they don't tell us what it's doing exactly. They give us a little hint there, but they don't really tell us. They don't give us access to those other prompts. What might be happening is that when it comes across a very difficult question, it can spawn more processes and do extra computation when the problem is harder. We don't know if it does that, but it could. If it does, then it's like a type 1 model with a type 2 system around it. Type 2 is like system 2 in the brain. The amount of computation you dedicate to a problem is variable. It can change, which means that if you come across a very difficult problem, you can dedicate more computation to it. You usually have few inputs. When you're a human looking down at a math problem, maybe it's something like a train just left Cincinnati, headed toward New York. It's going 88 miles per hour. And in 2 hours, it's going to change its speed to 101 miles per hour. When will it reach New York City? You have to go through various steps and think about this. And O1 is trying to do that, where it'll break the problem down, then go through various steps. But in that problem, there are few inputs. There's a city it's going from, a city it's going to, maybe a distance between those cities, and there's a train and it's got a speed and there's some time, 5, 6, 7 things. When you are consciously solving a problem, you can only juggle maybe 5, 6, 7 things in your head. Now, AI is going to go far beyond this someday. But this is different from type 1. When you look at an image of a dog or a cat, how many pixels are there in that image? Millions. That means you're processing millions of inputs. So type 1, fixed length computation, continuous math, millions of inputs. Maybe you're leveraging every experience you've ever had in your life. Type 2, variable length computation, fewer inputs, discrete logic and math. Now, those two, that separation there, it doesn't perfectly map onto anything in the world. This is a theoretical split, right? But I want you to use this as a rubric to think about problems in the world. System 1 is type 1. System 2 is type 2. All right. Yes. Yes. Logic, formal logic is type 2. Formal logic goes all the way back to the ancient Greeks, right? Let's say you have propositions. Maybe we'll call them A and B and C, and we learn things about A, B, and C. We learn maybe that A implies B. We also learn that maybe B implies not C. And we can deduce things from this. We can deduce that C probably implies not B, because if there was B, then there would not be C. And we can build up new bits of knowledge from what we know. Like if the grass is wet in the morning, then we know one of two things happens. Either the sprinkler was on or it rained last night. One of those two things happened, and we can build belief networks from this. We can also model systems. Like if you're going to model March Madness, the important thing to model at each step is who won which game. There will always be a winner to each game. And if you want to, bet on the winner, you should probably model who won each game and get good at that. Of course, it's next to impossible. Type 2 systems were all the rage until 2012. 2012 was this moment called the ImageNet moment. See, up until then, the best image recognizers were ones that people had done in a type 2 strategy. What that means is, let's say you want to make a thing that can recognize a cat from a dog. Someone would write a program that would go in and do edge detection. It would find all the edges. Then it would look for edges that were cat ear shaped and whisker shaped, or other ones that were like the shape of a dog with floppy ears, or a dog tail, or the dog tails and cat tails are different, and dog feet and cat feet are a little different. And you would write functions that'll look for these pieces, and then write another function that'll look for connecting those pieces. And you had people at every step deciding, I'm going to write this function to do this part of the problem. The other side, remember the word connectionism? Connectionism, type 1, is more about just making a big black box full of millions of little things that are going to act like brain cells. And if you train them with enough examples, they self-organize into something that gives you the right answer. Now, it might give you the right answer for the wrong reason, but who cares if you're still getting the right answer? Well, I'll tell you why you care. Somebody trained a visual recognizer to understand when it was looking at a husky or a wolf. Huskies and wolves are pretty similar. So they were pretty proud of themselves. 99.9% accurate, maybe. But they were actually secretly trying to prove another point. They had all these pictures of huskies and wolves. They trained the classifier. It was 99.9% accurate, but then they went one step further and they made the model show them how much attention it was paying to each pixel. What this means is which part of the image was it looking at to make its determination. Is this a husky or is this a wolf? It was looking at the snow in the background. It was getting the right answer for the wrong reason. In images, this is easy for us to understand. We all know that's the wrong reason. We all know intuitively that if you have an animal recognizer that's not looking at the animal, this thing is weak, it's brittle. You should not trust it. But what is the snow in the background for language? What's that? Accents? That's a good idea. I don't know. I know that there is snow in the background, metaphorically.
The frequency of letters.
Ooh, frequency of letters. That could be a big thing. Yes. Sometimes if you're asking your model to do something for you, you might get the right answer, not because of the meaning of the word, but the frequency of certain letters. Yep. If something gives you the right answer for the wrong reasons, you can't trust it any further than you can throw it. Imagine a guy who's in court and he's called to the stand and they make him put his hand on the Bible and say, "Do you swear to tell the truth, the whole truth, and nothing but the truth?" And he says, "Up to a point." "What point?" "The point where I start lying." Can you trust anything that comes out of that guy's mouth? No, because you don't know where the point is where he starts lying. GPT and all large language models will have a probability of venturing into falsehood. There's nothing inside the model that you can look at and point to, say, "Oh, it's lying now." No, it doesn't even know. It has no concept of truth or falsehood. Its only concept is, what's the next probable token? That's it. There's nothing else. What is the next token? Given all the tokens I've sent before, what's the next token? When I say a model in the machine learning sense or AI sense, and when you think about a model airplane or a model of anything, what is a model there for? Why do we have models? Why do we use them?
Things to represent larger objects in a smaller field.
Yes. So let's say you have a reality which is very difficult to understand because it's big or it takes a long time. Like, let's say we want to have a model of, the way stars work. Well, it would be nice to know what's going to happen to our star in 1 billion years or 10 billion years. We can either wait 10 billion years and find out, or we can have a model that runs faster, right? A model airplane, it is a model airplane because it acts like an airplane in some sense. It will fly. It moves a little quicker. Maybe it gets hit by the wind a little differently, but it still tries to mimic a real airplane. I want you to think about the word model as a model acts like the thing you're modeling. Sounds obvious, right? Sounds super obvious. But you got to keep that obvious thought in your head. A model should act like the thing you're modeling. If it doesn't, then it's not a good model. The parts of an airplane, a real airplane, are connected in the same way that the parts of this model are connected. You have a main fuselage. Stuck to it on the sides are wings. Underneath is the landing gear. You have a tail fin. You have all the main parts of the airplane represented here in the model. And those parts are connected in the same way as the real one. Remember graph theory, the connectedness of things? The connectedness of things is very important. If we took one of those wings and said, instead of connecting it to the fuselage, we're going to connect it somewhere else, maybe underneath on the landing gear, it would not function the same. It would have major problems. If you want to use the model to learn anything at all about actual airplanes, the parts have to be connected the way they are on the real plane. This is a model of a person learning to walk. They took this thing, it's a simplification of a human. It's got a head, 2 arms, 2 legs, feet, torso. So it's a simplification, but the main parts of a person are there. And they're connected in the same way as they are on a real person. They also put this thing, this AI, in an environment with gravity. Gravity equal to Earth. 9.8 meters per second per second. And they gave it a goal. The goal was to move yourself in that direction. And it would get rewarded when it moved itself faster in that one direction. When it started, it was flopping around like a really, really drunk person trying to move. After a few, years of virtual time, sped up, it was able to, walk like this. And then eventually it was walking more normal and eventually run. I saw some footage of it running and it was doing this weird thing with its arm where it run like this. But it learned over time. It can teach us something about human walking. It can teach us, even though it's weird and different, it can teach us a little bit about what's going on in the human brain when you're a little kid and you're learning to walk. And we can learn something about human walking because it has the parts of a human body and they're connected in the right way. They did another experiment where they said, hey, let's use other body shapes. Some of them were able to walk much faster than the human. No torso, maybe you get rid of the feet, maybe you have 4 legs instead of 2. Even though this may be interesting, this doesn't teach us about human walking. We can learn a lot, but we're not learning about human walking because there's not the same parts and they're not connected the same as the human parts. It's not the same thing, and it's not connected the same. It's not a model of human walking. Any questions before we move on? All right, now let's tie all this back to language. Jack and Jill went up the hill. What is the topology of this sentence? There's more than one answer. I'm not doing Euler characteristics for this stuff. Is that what you're talking about? So let's think about it as a graph, things that are connected.
Hill, a line from Jill to the hill, and that line would represent like going up the hill. Like,
Very good. I like the way you're thinking. Does I see a hand over here?
Same thing, like Jack and Jill probably very closely connected, maybe to like went, since they went somewhere and then went connected to a hill.
Yeah. Bringing in the verbs. I like it.
Instead of separating Jack and Jill, I feel like they have to go together, so they could be a combined.
I like that too. I'm going to put together what all three of you said. You all had right answers, and they all go into what's called parsing. And there's two main kinds of parsing. Constituency and dependency parsing. We do constituency first. Constituency parsing will think of an entire sentence or thought as a binary tree. So we have the whole sentence, we'll just call it S. And we'll break it down into we're going to break it down a couple ways. So we'll have a verb phrase, and the verb phrase is going to have a noun phrase and a verb. And a prepositional phrase. Me. I'm running out of room here, so I'm going to write small at the bottom here. Okay. The idea is to take any sentence and break it down, and then take those parts and break them down, and take those parts and break them down, and keep doing that until you get individual words. So Jack and Jill went is the verb phrase. Inside that verb phrase, you have a noun phrase and a verb. The noun phrase is Jack and Jill. The verb is went. On the right here, we have a prepositional phrase, up the hill, which we can further break down into up, a preposition, and another noun phrase, the hill. The hill is a determinant, the, and hill, noun. You could say that the topology or the graph structure of this sentence is represented by this tree, this binary branching tree. There are arguments that linguists will have with each other about how to exactly define each part of the tree. That's unimportant. I wanted you to have an idea in general of what a constituency parse is. Now, let's look at a dependency parse. There's actually a different sentence. So I'm going to parse out the same sentence, but using this kind of tree. This is the dependency parse of the same sentence. I put went and up together. How many of you speak other languages? Raise your hands again. In some other language, I want you to say went up.
Subo, I guess.
Someone else, one other language, come on. Say it. Shanshu. Oh. So for how many of those was it one word? And how many was it two? So one word, subir. One word. And how many was it two? None of them, right? In English, went up is two words. In some other languages, it might be two words, but oftentimes it's just one word because this is really one concept, right? Went up. In English, we use two words, but it's really one concept. So the main concept or verb concept of a sentence becomes the root of a dependency tree. Think about a tree pointed downwards with the root at the top. I don't know why we draw it this way, it's just how we do. So went up, that's the root of the tree. That root and every node actually will have things under it until you get to the leaves. And when some verb has things under it, we call them arguments. Just like a function in math or computer science, a function has arguments. And went up, this one has two arguments. It's got a couple people that are doing the going up, and it's got a place where they're going up to, or they're going up on. So you have the place, which is hill. And it's not just a hill, it's the hill. The modifies hill. Hill is an argument for went up. And then you have Jack and Jill. They're both under and. And is what's combining Jack and Jill. We don't have any sense that, Jack's going up the hill, but Jill's not. No, they're both doing the same thing. We don't even know if one of them is going up the hill faster or slower than the other. They're both combined.
So when you have a noun that's a non-proper noun, does it always have an argument for something like the, a, there?
No, depends on the language. We want to always think about things that are cross-linguistic. There are accidents in English sometimes, but like, I believe you don't always have to say the or in Russian. Isn't that right, Murat? The or can just be left out. Right? Well, he was asking, when you have a noun like hill, does it always have a the or an below it? But you don't need that in Russian. Yeah. Jack and Jill went uphill, right? Yeah. We want to think about the core concepts. There's something that Noam Chomsky, who is the father of modern linguistics, Noam Chomsky had this term. Mental ease. Whether you speak English, Japanese, Chinese, Korean, Swahili, in your head, something's going on. Whatever that is, that's what we're trying to get at. That's what we understand, what we want to understand in this course. The way you write those words in your language is like a projection. There's something in your head, mental ease, and you choose to cast it like a shadow down into a sequence of words in your language. But we want to understand where it comes from. I want to hear from you guys what you think of these two ways of parsing the same sentence. Is one of them better? Is one of them worse? Are they just different?
Dependency tree seems way more efficient than constituency tree.
More efficient, yes.
I guess consistency, if you're trying to get deep into like debug a certain part of the sentence, it's useful because I guess it kind of separates it in a more specific way, but yeah, I agree, it's more efficient, quicker to understand dependency.
Dependency feels like more natural, like how I think about stuff.
Dependency feels like less specifically constrained to a certain language and more like concepts of the sentence.
Wow, I've never had everyone agree with me so much. That's fantastic.
It feels like for OPL, we have like expression trees and all that stuff. Feels like that.
Tell everybody what OPL is.
We're told that there's like expression trees for how the
Inheritance?
or expression.
Okay.
A with B plus 2. And we'll take this.
So I love dependency trees. I absolutely love them. I hate constituency parses. I hate them. Now, many people do love them. And you should be aware of those people and learn from them when you can.
Could a dependency tree be more ambiguous in terms of like creating the original sentence for the dependency tree than the constituency tree?
Both can be ambiguous. There are cases where I've seen linguists disagree with each other. And it doesn't matter if you're in this domain or that domain. There's always room for people to disagree. Ambiguity often comes out because of polysemy, the fact that the same word can mean multiple things. Sometimes a word can have like 20 definitions. And if you're looking in the dictionary, you see like definition 17 and 14. To you, they're the same definition, but to other people, they're different. Even though all of us speak English, we don't all speak the same English. Everybody has a little bit different understanding of words, and you don't even know it. Most of your life, you hear words, you think you understand them, and you're not going to everybody for every word. What did you mean by this? What did you mean by that? No one does that. You just assume you got it and you move on. Have you ever heard the phrase to beg the question? That begs the question. How many of you have heard that phrase? What does it mean? Someone define it for me.
Means that like whatever is begging the question is like it's like, okay, now I have to ask this question because of what you said or something. It's like it's so obvious, it's like painfully obvious that I have to ask this question.
So it's the same as that raises the question.
Well, it's very simple.
Is that what you're going to say?
I was gonna say, it raises the question.
The second question necessarily follows.
Okay. This is something that's changed in my lifetime. Now it seems to mean what you guys said, to elicit a specific question as a reaction or response, a question that begs a question to be answered. But the old one was, okay, to ignore a question under the assumption it has already been answered. It comes from a translation of an Aristotelian phrase rendered as beg the question, but meaning assume the conclusion. I wonder if any of these examples are specific to that one. Say, the U.S. Postal Service says that a personal letter delivery is at an all-time low, which begs the question, are open letters the only kind the future will know? I don't know why that one's there. Okay. The older definition is hard to get a grasp on because it's something we don't talk about too much in conversation. Like if someone were to say that begs the question, when I was a little kid, it would not have meant that raises the question. It would mean you're asking a question that assumes something. You're begging your own question. Like if you're a politician and someone comes up to you and asks you a question like, why do you hate this constituency so much? Why do you hate these people so much? Well, that person probably doesn't hate those people, but now they're stuck in this question of how do I answer? There's no right answer to the question. The phrase to beg the question changed in my lifetime. And it's because it went out of use for a little while. Then when it came back and people started hearing it on the radio, I remember hearing it on the radio in the early 2000s, used the wrong way. And I was like, oh no, this is going to stick because it intuitively makes more sense. It sounds better. So when you hear something and you don't know what it means, you assume something. And if everyone around you assumes the same thing, that is the new meaning. You guys may also know that the word literally has changed. When people say literally now, they mean figuratively. I'm like literally starving. You know, you're not. You're figuratively starving. And we have a word for that. The word is figuratively. But now you've used the opposite of figuratively as the word we already had. Now we're losing it. We lost a whole word because of you guys, because of your generation. Anyway, I don't want to complain. I appreciate the fact the language always changes, and that's beautiful. But I just wanted to make the point. We don't even all speak the same English. There are some words, use of these words oftentimes can show where you grew up. Maybe things have changed now, but when I was a kid, just what you call, like when you want to go get what we call, a drink that has carbonation in it and some sugar, I want to hear what you guys call this thing. Just shout out some.
Pop.
Pop, there's a pop. What else is there?
Coke.
Some people just say Coke. If they want a Pepsi, they ask for a Coke, but they mean a Pepsi. Or a Sprite, but they call it a Coke. In the 80s and late 70s in the Boston area where I'm from, we'd oftentimes say tonic. That meant a Coke. Like if I wanted a Coke, I would ask for a tonic and I'd get a Coke because that's what I wanted. How many words for sneakers can you guys think of? Sneakers, kicks, tennis shoes. There's a couple other out there. How many words for awesome? Sick. Fire. Lit. Can you name any of those terms from what?
5 big booms.
What are the 5 big booms? I never.
Boom.
I've never heard this. Can you name any from your parents or your grandparents' generation that you don't use anymore? Rad. Swanky. There you go. Swag. Nifty. Peachy. Copacetic.
All that in a bag of chips.
All that in a bag of chips. Okay. I haven't heard that one. No. Language is always changing. Going from the way we write it. Now, this sentence is very similar. Jack and Jill are also featured prominently here, but this time Jack gave Jill a book. Going from that to the dependency parse, which remember, I love dependency parses. That's what we'll focus on the rest of the course. Yes?
How do we go about parsing that as a dependency?
Yeah, it's hard. One thing to remember is that with the dependency parse, meaning of each part and how they're connected is what's important. Just like that airplane, you want the wings connected to the fuselage, not somewhere else. So gave is the main verb of this sentence. That's the thing, what without that thing, you wouldn't have said the sentence in the first place, right? It's a verb. Verb is the organizing principle of a thought. Verb, action, or being. So gave, it's got to be the root. That's how you start. You have to find the root. Start there. Now, gave. What's going on with gave? Gave is a movement. One linguist friend of mine, a guy named Dr. Connor Quinn, he's my favorite linguist in the world. He's brilliant. He said that every sentence that a human utters is an analogy to basic physics. And there's 2 kinds of physics that would have mattered to early people. One is movement of something. Like if someone gives you something or someone throws a rock at you, there's a movement of an object. Give is a movement of an object. The other kind of physics is light. Light shines on things. And apart from light shining on things and physics of something moving, that's like all human thought can be somehow compressed into those 2 things. Give is going to have a giver, a gift, and a recipient. So if Jack gave Jill a book, Jack is the giver, Jill is the recipient, and the book is the gift. So you got 3 arguments for that function, for that verb.
Does that go back to constituency, just swapping out the words for the?
No, the constituency parse is all about, I have an idea, can I break that idea into a sub-idea? But phrase-wise, noun phrase, or parts, prepositional phrase and noun phrase and whatever. And you don't even think about arguments of verbs.
So I guess, are you losing information when you go from a sentence to a parse tree? Because
No.
No.
If you are losing, it's not lossy. It's information that's inherent that you can get back. So if you did your dependency parse tree correctly, you should be able to perfectly reconstruct the original sentence, or at the very least, construct a sentence with equal meaning. Everything about the meaning needs to be in your dependency tree somewhere. There should be 0 confusion about the meaning. Now, this is hard because sometimes in a sentence, we have double entendres. We'll see how to deal with that next time. We got to go. Last question.
How, like, for this example, you grouped both like verbs, I guess, went up, right? You grouped those 2 words, which is like an egg sketch. Like you knew those went together. How do you handle sentences that have multiple words? Like words like
You try your best to come up with rules regarding prepositions. It's going to be different for different languages. There's no one right answer.